for details, please refer to the paper. And here we show the performance. We built string vector with the new pointer mechanism. We test the 5 benchmark of common vector operations. As shown, the overhead is amortized when the element size grows larger than 32 bytes. And for common applications such as RSS reader, the bit size may be 400 bytes. And so we believe for real-world applications, the point overhead is not so significant. And exceptional is the pushback benchmark because the compiler does some aggressive optimization for Slim. Then let's move on to the L3 to enroll the clouds. Device and cloud in L3 can be modeled as a pair of L2 sharing the same universal address space. More specifically, clouds manage the universal address space universal address allocation, and all the data is available in clouds. The device side polypointer load miss is pumped to the cloud for data, and for consistency maintenance, we implement a message passing way. Updates from both sides are packed in a notification message and dispatched to each other. And an alternative is to move on to the shared key value store. And as you can see, polypointer load miss here will incur visible latency. We then employ the promise asynchronous mechanism to settle this. Recall the inverted index building. The final step is to use the get interface to query about the keywords. This will block the thread if the data is not immediately available locally. So we rewrite the get interface with promise object. The interface will return a promise object instead of the real value immediately, and the real value may or may not available when a user got the promise object. The programmer can bind a callback function to this object and continue other jobs. When the real value reaches, the callback function will be called to continue with the program logic consuming the real value. For future work, we want to investigate more about the synchronous programming model. Currently, promise is not by no means a free lunch. It will incur some complexity, such as the vector of promise objects or promise object of vector. And we want to also rethink the choosing of programming language because the pointer and the swizzling techniques incurs complexity in C++. And we want to investigate more about the bidirectional case. For email clients, there can be user deletion and cloud appending simultaneously. And to summarize the talk, we first proposed the Slim data structure to serve as a mobile plus cloud application partition point. And then we introduced the policy which user can use to alter behaviors and implement different functionality. Then we introduced how to program with these two things. We need the split code and the same data structure bridges in the middle. Finally, we introduced a promise mechanism which binds a relay function for return value to achieve the asynchronous message passing. That's all. Thank you.
But I'm very interested about the Slim framework. I described it as a framework or a middleware.
Yes, we appears like a library and some sort of the middleware.
Okay, so I have two questions. One question is the Slim library get the programmers easier to program their activities?
Yes.
Is this library let the program easier?
It's hard to say if it's easy because we changed the stateless to event-driven way. Someone may like it, someone may not. So it's hard to say if it's easy.
And I wonder how complex is your logic between the cloud to the websites like the RSS and other sites? How is the complexity in your code?
Yes, the partition work is now done by hand, and part of the logic is dispatched. Typically, extensive computation are shipped to the cloud, and in the for the IIS case, you have seen. Yeah, in the IIS case, this is traditional code, and for WinSlim, this is the device side code. A shared data structure and a callback function. That's all for the update logic.
So you will develop a different code between the Windows, assume between Yahoo, between CNN and others.
No,
individual.
These are only the sources for the RSS. Code are reside in the device and the cloud.
Okay.
So the first question is that online.
So the second question is that did your Steam library have a present move on the performance? So in the traditional way, they will put RSS in somehow 5 seconds, and use this Steam library, it will get longer, perhaps over 30 seconds. So how is the performance of your library?
The extensive computation are shifted to the cloud, which is one of the design goal. And the fetching job is done by cloud, which should be faster than just doing that in the device. And only the updates are conveyed by means of the same shared data structure to the device. So in the device side, you receive continuous updates instead of your periodically fetch the XML, pass it, and then find new ones. In this case, we've done some emulation, and the most heavy part in the ISS reading case is the XM parsing. So for this case, we have some performance gains.
How do you push back?
How does the cloud push back the computation to the cloud?
How does
the cloud server push the result back to the client?
Yes, it's a consistent thing. So currently, we have implemented a message passing way. If the update happens in the cloud, it will package a notification message and dispatch to the device. The device will receive that.
How does the client server keep in touch on the client? If the server doesn't submit those various packages push back?
Devices are always connected to the cloud with the shared data.